Equilibrium constant. So far we've been using KEQ as a generic constant. Equilibrium constants quantify the relative amounts of reactants and products represented at equilibrium. Kc is an equilibrium constant when measuring concentrations of aqueous solutions in gases. So I want to underline concentrations of aqueous solutions in gases. And it's basically what we've been doing before. Okay, it's the same exact thing. It excludes solids and liquids, but includes gases and aqueous, because this has to do with concentrations. Kp is an equilibrium constant when measuring partial pressures of only gases. So we're dealing with pressure in this case, and it only refers to gases. So this is how we write it. Kp is the partial pressures, which I'm circling here, at equilibrium raised to a certain exponent based on their coefficients in the reaction. Again, since K is specific to temperature, K changes as temperature changes. There is a relationship between Kp and Kc when only dealing with gases. When trying to find Kc, we know that in the ideal gas law, PV equals nRT. Well, since concentration equals N, which is moles, divided by volume, P equals P divided by R times T, where we know that R equals 0.0821, and this is temperature, and it has to be in Kelvin. Okay, so when we plug everything in, the concentration times R times T equals P. From that we can derive this equation here, where the constant at pressure equals the constant for concentration at equilibrium times R times T raised to change in number of moles. Number of moles, define this part of the equation. You take the number of moles of product gas, again I'm going to circle gases here, subtracted from the number of moles of reactant. Okay, this is gas situations only. Okay, so here we have some practice here where we have 2 moles of gas on this side, and we have 4 moles of gas on the other side, and we get -2 because 2 minus 4 gives us that. We have 2 moles on the product side, and we have 2 moles, so therefore 2 minus 2 equals 0. On this side, we're going to eliminate the solid. We have 1 mole of gas on the product, so therefore 1 minus 0 equals 1. And the last one, we have 1 mole here. We don't care about this. So 1 minus 0 equals 1 mole. Here's an example problem. Okay, notice how all these are gases. And I have a Kp situation. Okay? Now what I'm going to ask you to do is try to calculate the Kc for this reaction at the same temperature. So here's your solution. You know that Kp equals Kc times R times T raised to the delta N power. Delta N, you know, is 2 minus 1 because there's 2 moles over here and 1 mole over there. Plug everything in and we solve for Kc and we get this is our value. Now notice all these, this is again a gas situation. Will not work for aqueous solutions. I'll go ahead and underline that. Okay, so here's a couple different scenarios when we reverse reactions or when we multiply a reaction by a coefficient or we add reactions. What do we do? Okay, so let's take a look. So the first thing we do is we have the original equation, and then we take a look at what we do to that equation. So in this equation here's our Kc value, okay? When we reverse the equation, here's our Kc expression. So all we did when we reversed the reaction is we flip-flop these, and therefore when we calculate K, we merely take the reciprocal of it. How about when we multiply the reactions? Again, here's our original equation. Here's our second equation. What do? We multiply the entire thing by 2, okay? So when we do that, here's our Kc expression. But all we did is we took this expression and we raised it to the power of 2. So here's the rule. When multiplying a reaction, merely raising the original Kq to the same power, okay? So this 2 pertains to multiplying this equation by 2, okay? So these two go together, okay? Final thing, when combining reactions, okay, here are the two reactions. We know when we combine these, our net equation, we get these because these guys cancel out, okay, and we get this. But what happens to our Kc value? Well, something very interesting happens when you multiply the expressions together. Here is our Kc1, this is our Kc2, this is our Kc1 times Kc2. And when we get that, we get our Kc3. This right here is the expression for this. This is what we're looking for. So here's a rule of thumb. When multiplying, or when adding the reactions, you simply multiply the K values. Okay? You multiply the K values from each reaction to get the combined net reaction. So in a nutshell, in summary, if you reverse a reaction, you invert or take the reciprocal of K. When multiplying a reaction by a coefficient, you raise the coefficient as a power, and actions, you simply multiply their K's.